Hello and welcome to our 25th session. In this session we're going to continue our discussion of the bipolar junction transistor, and we're going to take a step back a little bit and review some of the issues that I don't think were covered quite as well as I would have liked, specifically mass action, reverse active mode, and law of the junction as they pertain to the BJT, and that'll take a significant amount of our time this session, and hopefully we'll be able to move on toward the latter part of the session into second order effects. And the things we're going to be looking at there are the early voltage, high level injection, and more importantly, and we'll wind this up either this or probably next session, in the heterojunction bipolar transistor. And then after all that, and we'll look at a few word problems, we'll be able to flip over to the metal oxide semiconductor and the MOS field effect transistor on the right side of the device structure tree. So probably at least this session, next session, and maybe one more on the bipolar junction transistor before we move over to the metal oxide semiconductor field effect transistor side of the tree. But first, let's listen to a marvelous production of the Gypsy Scene from Verdi's La Traviata. We'll see you back in about 3 minutes. Okay, so this is a list. It's a rather extensive list of some of the topics we'll be covering in today's session. This will take us absolutely, I'm sure, will take us into section 26 and maybe even into section 27. So I'd like to start with tying up some loose ends in junctions, going back to the law of the junction, the law of mass action in a non-equilibrium situation, both in forward bias, which is certainly non-equilibrium, and reverse bias, which is also non-equilibrium, even though the currents in reverse bias are very low. Then we'll take a look at the reverse active mode. We took a look a little bit at these modes. The forward active is the main mode, the saturation mode, the reverse active mode, and the cutoff mode, which we haven't really discussed very much. Then I'd like to try to make the case for why we have to make the base region short, as narrow as possible. So we'll take a look at that. And then we'll go on to something which is a little bit more mathematical, the current components in a general case. And this is going to take a fair amount of effort, and we'll just see how that goes. When we finish that up, hopefully we'll get close today. Then we'll look at second order effects, and I've divided the second order effects into two main categories: the bad news, things that degrade performance. And we'll talk about the early effect, the bandwidth modulation, high level injection, and then low level injection. So we'll talk about these things which we have to overcome, and then the good news, how do we overcome them? How do we make these devices perform better? We'll talk about non-uniform base doping, which is a relatively small fix, but the big fix is the heterojunction HBT, heterojunction bipolar transistor. We'll talk about that in some detail. And I don't know how far we'll get today, but we'll end today's discussion with a clip from Mozart's Don Giovanni Madamina. Okay, let's look at the law of the junction revisited. So here we see a PN junction. Of course, the bipolar junction transistor has two of these bad boys. The PN junction in forward bias. How do we know that it's forward bias, and how do we know that it's in non-equilibrium? So let's address the second of those issues first. How do we know it's non-equilibrium? You know it's non-equilibrium because the Fermi level is not straight and horizontal. And you can see that we have two Fermi levels here, and therefore there is a depletion region right here. We have band bending, and we have an electric field. The electric field always goes from positive to negative. Therefore, the positive is on the right side of the depletion region. These are positive donor ions that have given up an electron and become positive fixed ions embedded in the lattice. In the p side, we have negative arsenic ions which have an accepted electron, and they become also fixed in the lattice. So positive to negative, the field goes from right to left in the negative direction. In forward bias, we overcome that, at least partially, by putting on an external field which goes in the opposite direction. So therefore we put the plus sign on the left side and the minus side on the right side. So the external electric field goes from left to right in the positive direction. Now, if it were in equilibrium and we had one Fermi level, which was straight and horizontal, we would have the law of mass action, so that NP is equal to NI squared, and that is not true when we have non-equilibrium. However, in the bulk, we can write that the number of holes referenced to intrinsic is equal to the number of intrinsic holes multiplied by the exponential of how far in this case, we'll start with P, how far the intrinsic is above the quasi-Fermi level on the P side. So this number here is positive. E sub I is greater than E sub FP. So that's why we have a positive number here. So the number of holes will be much greater than the number of intrinsic electrons or holes. N sub I is 10 to the 10th at room temperature. It looks to me like we have about 10 to the 17th or so. So this number here will be about plus 0.42. Same thing on the N side. It looks like it's a little bit smaller, but we're going to say it's basically the same thing, about 0.42. The quasi-Fermi level on the N side is above E sub I, which is why this is reversed here. E sub Fn minus E sub I. So this is a positive number also. Let's say it's about 0.42 eV. So we have the same number, more or less, of electrons and holes. And we can multiply the left side together. We multiply the right side together. And the E sub i's cancel out. So we have E sub Fn, which is positive, minus E sub Fp. And we see that E sub Fn minus E sub Fp is equal to the applied voltage, V sub A. And, of course, in a bipolar junction transistor, if this is the emitter and this is the base, this voltage V sub A will be the forward bias, the bias between the emitter and the base, and it is positive. And let's just say it's 0.6 volts. That's an easy number because 0.6 divided by 0.026 is 10 to the 10th. And then we get the Pn product is not equal to e to the 10 to the 20th. It's now equal to 10 to the 30th. And we apply the same reasoning to the base side. This was on the this is generally true. Now we apply it to the base side of the junction right here. We would say that this is doped 10 to the 17th on the base side, 10 to the 19th on the emitter side. So the number of holes, P sub n, this is the number of holes on the N side, is equal to the P sub n product divided by the equilibrium number of electrons on the base side, which is 10 to the 17th, because that's what it's doped. It's doped 10 to the 17th, so the majority carriers are electrons, the minority carriers are holes, and therefore we find the number of minority holes are the Pn product divided by the number of equilibrium electrons on the base side, and we find that it is we get 10 to the 13th. It was 10 to the 3rd, but we boosted by 10 to the 10th, so 10 to the 10th multiplied by 10 to the 3rd is 10 to the 13th. So now we do the same thing on the emitter side. And on the emitter side, which is P-doped, at the depletion region edge, we have the same Pn product, 10 to the 30th, divided by the majority carriers, the PPs, if you will, in the emitter, which is 10 to the 19th, and we get 10 to the 11th. So the boost on the base side is 10 to the 13th, the boost on the emitter side is 10 to the 11th, and that, of course, I shouldn't say of course, that's where the beta comes from. There's 2 orders of magnitude, because we get more hole current, which flows from the emitter to the base and eventually is collected at the collector, then we get electron current, which comes from the base into the emitter, and that's the input current. This will produce an input current. This will produce an output current. The output current is 100 times bigger than the input current, and that is a very good thing. So now let's consider two junctions. We just looked at the emitter-base junction, heavily doped emitter, moderately doped base. Now let's do the same thing at the base collector junction. At the base collector junction, we do the same deal, 0.6 volts, 10 to the 10th boost, and let's see what we get. Okay, so the boost is the same, 10 to the 30th. So the excess holes at the left junction we found is 10 to the 13th. That's what we already did. I just repeated it, but you should know that. Okay, and the excess holes on the right junction, we do exactly the same thing. Notice we have N0 in the base. At the left junction, we have N0, which is the equilibrium number of majority electrons in the base, also at the right junction. So we have exactly the same number of minority holes at the right junction than we do at the left junction. That is not intuitively obvious, but it's important. And that begs an interesting question. It just seems like it doesn't matter what the doping is in the collector. I still get the same thing. Suppose then we take it one step further. We go, okay, instead of 10 to the 15th, I want to dope this guy 10 to the 13th. So there'll be 6 orders of magnitude difference between the emitter, which is 10 to the 19th, and the collector, which is now 10 to the 13th. Is that going to change this? Not according to the theory. We're still going to have 10 to the 13th minority holes in the base, even if the collector is very lightly doped. Let's take it one step further. Keep this at 10 to the 13th, but now up the forward. I should make a point here, which I perhaps neglected. I should have not neglected it if I did. We also, we also have a forward bias at this junction of 0.6 volts. Forward bias at each junction. Okay, I didn't. Perhaps I should have explicitly emphasized that. 0.6 volts forward bias here, 0.6 volts forward bias here. The number of minority holes in the base at each junction only depends on the doping in the base and the forward bias. So suppose now I keep this really lightly doped, 10 to the 13th, and I up the forward bias at this junction to about 1 volt. This is not going to be 10 to the 10th. This is going to be about 10 to the 16th. You can work it out. It's very simple. The whole thing here is going to be like something like 10 to the 40th. Is that going to change this? Yeah, it's going to increase it, but it still will only depend on the doping in the base. And if I had 1 volt forward bias here, I would still have the same number of minority holes in the base at this point, at the edge of the depletion region, as I do at this point. We say, where do all these holes come from? It's very lightly doped. Well, they're there. They come somehow they pull them out. It's kind of interesting because we're going to see something somewhat analogous when we talk about a metal oxide semiconductor. It's not the same, but the concepts are similar. We're going to be able, for example, to take a P-type silicon substrate, and we're going to apply an electric field, which is basically what we're doing here. Applying a voltage applies an internal electric field, and we're going to be able to suck up minority carriers, which in this case will be electrons, if it's P-type, and we're going to be able to put those electrons right at the surface. So, example, if we have a 10 to the 17th doped silicon in a metal oxide semiconductor structure, we're going to be able to produce an extremely thin layer, almost a monolayer, just maybe a few tens of monolayers right at the surface. And not only will be able to produce this monolayer of electrons, we're going to be able to produce a monolayer of density 10 to the 17th, the same density that we had in the p-type silicon. If the p-type silicon is doped 10 to the 17th, we're going to be able to produce at the surface, it won't be a junction, it will be a surface of 10 to the 10th or 10 to the 17th electrons. And that actually boggles the mind. So we're going to see that in just a little bit. Okay, so now let's go to the reverse bias. First, let's go back to the picture all the way back here. This is the forward bias. We have an external electric field which counterbalances or works against the internal electric field. The internal electric field is in the negative direction. The external electric field is in the positive direction. In reverse bias, the external electric field is also in the negative direction, plus to minus, right to left. And of course, the internal electric field is also from right to left in the negative direction. And what happens here is we pull the P up rather dramatically to increase the barrier on the P side, and we push the N side down to increase the barrier on the N side. And what happens in that case is now the quasi-Fermi level on the P side is above the quasi-Fermi level on the N side. Notice here, quasi level on the P side was below the quasi level on the N side. Now, these two equations are exactly the same because these are on the bulk for the reverse bias, for the forward bias. And of course, they're the same if it was equilibrium, but in equilibrium, this would be just one Fermi level. Here, there's two Fermi levels. So these equations haven't changed. They're exactly the same. The number of holes is given by n sub I, E sub I minus E sub F, because E sub I is above E sub F. So this is a positive number here. Let's say about 0.42 eV, 10 to the 17th. And the N, of course, the Fermi level on the N side is above E sub I. This doesn't really look like it's 0.42, but trust me, we're going to assume it is. It's not terribly important. And we get exactly the same equation here, except now we have, and this should be a, sorry for the hesitation there. The E sub i's cancel out, plus E sub I minus E sub I, E sub Fn over here, minus E sub Fp. And that's the same equation, except E sub Fp is higher than E sub Fn. So this number here is negative. And therefore we have a minus applied voltage V sub N. So in this case, we write the same equation here. I don't know why I put in 1 volt here, but okay, just for fun. This should be 0.6 volts, I believe. I'm not sure. Oh, you can work it out for yourself. It's not important. We get a P sub N product, which is essentially 0. It is so small that it's not worth talking about. And that tells us something that we already know. In reverse bias, there are essentially, and this is the depletion region, there are essentially no mobile charges whatsoever. Essentially 0. I just want to make one other point here, which I should have made back here. And that is, where do I make that point? I should make that point. Okay. in forward bias, if I didn't, oh, here it is. Forward bias subjects the depletion region to charge recombination. And that's an important point, because what we have here, and if it was an equilibrium, we would have approximately intrinsic 10 to the 10th, and now we've got much more than that. We actually have I should say n sub I squared would be 10 to the 20th in the depletion region. In forward bias, even at 0.6 volts, we have 10 to the 30th. 10 to the 30th is way higher than equilibrium would tend to dictate, and we've thrown this device into a sort of a chaotic situation. We put in many, many more mobile charges than the thing wants, and therefore the structure says, I need to try to restore equilibrium, and the way to restore equilibrium is through charge recombination. It's basically applied Le Chatelier's principle. Stress a system, the system will try to restore itself to its pristine condition. In the reverse bias, I've sucked out mobile charges way beyond what I would expect from equilibrium, and therefore we have not recombination. Reverse bias subjects the depletion region to charge generation. So in the one hand, in the forward bias, we have a tendency to recombination. There's a recombination current. And in reverse bias, there's a tendency toward charge generation. We have a generation current, and that will become important for second order effects. And I talk about this quite in detail. We didn't go over it in our sessions. This is the Shockley-Hole-Reed theory, or is it Shockley-Reed-Hole? I forget. Whatever it is, Shockley's name is first, because Shockley always makes sure that his name goes first. That's Bill Shockley. All right, we won't get into that further. Okay, so let's use these principles to talk a little bit about this thing called reverse active mode. And this is, I hope it's revisited. I think it is, but I'm not sure. So let's look at the current components in the forward active. Why is this forward active the good stuff? Well, we like it to be because number one represents holes that are injected from the emitter to the base and travel in a journey across the base and are collected in the collector. Hopefully 2 is equal to 1, and that's true if we don't have any recombination in the base. Component number 5 is electrons that are injected from the base into the emitter. This difference between 1 and 2 is 1 is about 100 times more than 5. Why did I say 2? It's 5. Component 1 is about 100 times more than component 5 because of the doping differences. And here we have 10 to the 19th, here we have 10 to the 17th. Component 6 represents electrons which are injected from the base into the collector. Now, why isn't this bigger? In fact, it should be bigger because we're going from a heavy to a light. The reason is in the forward active mode, the left side is plus and the right side is minus. And a minus will push electrons back, repel electrons, where the plus sign here will attract electrons like a vacuum cleaner will suck them up. And of course, holes, it's exactly the opposite. The holes at this junction, which represents component 2, will be sucked up by the negative voltage. In reverse active, components 3 and 4 become important. In forward active, they are very small. Why are they very small? Because the doping differential. This is light and this is moderate. So we have a very small excess charge distribution at this junction compared to component 6. However, if we bias the base collector junction in the forward mode, plus, minus, we can now have a large component number 3, and notice that number 1, which is reverse bias, becomes quite small. And again, if the base is pure and pristine, all of the charge that is injected from the collector into the base winds up at the emitter, and that becomes my output. And now my input also becomes quite a bit larger, because now I have electrons that are injected from the N base into the P collector, and now because I have a plus sign here, those guys are grabbed up. So component 6 goes way up, component 3 goes up, and I have a relatively poor operation point. In fact, I've got very little good that comes out of this. That's why it's called the crazy mode. Reverse active mode, but it's also the insane mode. Okay, here's the general rule. Injection from high doping to lower doping results in higher excess charge concentrations and higher currents. And I should have put this in bold, when, and this is the critical thing, when compared to injection from low to high. So high to low results in higher currents, higher excess charges, but only when compared to that same junction going from low to high. Okay, so now I want to make a couple of points about why it's important to fabricate the transistor with a really narrow base. And this is the first one. We're going to look at it I'm going to tackle from a couple of different perspectives. But this is a picture, a cartoon, emitter, base, collector. The emitter is wide, collector is wide, and the base is narrow, and that is exactly the way it should be. We can consider the emitter and the collector basically being receptacles for the injected charge. The collector is a receptacle for charge which comes from the emitter. The emitter is a receptacle for charge which comes from the base, and a little bit, if it's in forward active mode, which comes from the collector. However, if I have a wide base or a very large, very small tau, the time that it takes to recombine, this diffusion current will drop off very quickly and essentially go to zero, and the current will be picked up by drift. So at this point, if you look at the actually, I should have perhaps said, instead of the differential current density, the excess charge concentration, if the excess charge concentration goes to zero, the slope goes to zero, and therefore the current, the diffusion current, goes to zero. So from here, from this point on, it's all drift. But the idea is this current here is modulated, is changed by the base injection of electrons. I make the forward bias a little bit larger, and therefore the current goes up. I make the forward bias a little bit less. The diffusion current, I should have emphasized the word, diffusion current goes down. We lose all of that modulation. We use the control when it goes to zero. It's all drift, and basically I was going to make the pun, it drifts on, but it's not very terribly useful. So this is the base, and having a very large base, I lose control at the collector from what happens at the base emitter junction. And that is not a good thing at all. And now let's look at the situation where I don't have a small recombination time. I have an infinite recombination time. And therefore I have straight lines. And this cartoon shows these straight lines as a function of the bias at the base collector junction. This would be equilibrium, where at the junction itself, the excess charge go to zero. That's basically what we have in a p-n junction. Here, I put a forward bias, so the excess charge distribution at the base collector now is higher, which produces much less collector current. And here, I have a relatively large reverse bias, so the excess charge carrier distribution at the junction becomes less than zero. In fact, it becomes equal to the minority carrier concentration in the base. If the minority carrier concentration in the base is 10 to the third, this right here becomes minus 10 to the third for the excess. And that's a good thing, because look at the slopes. The slope here is not so high. The slope here is very high. Which one gives us bigger current? The current depends on the slope. This will give a small current. In fact, if it was horizontal, there would be no current. That is in the saturation mode. So this will give a much higher current in reverse bias than this one, which is representative of forward bias. Now we can do the same thing by keeping the bias at the base collector junction constant, but just varying the width, going from W1, which is relatively narrow, to W2, which is wider, to W3, which is wider yet. And we see at the end of the journey here, compared to the end of the journey here, which slope is higher? It's pretty clear. This guy has a much narrower slope, much shallower slope, less current than the shorter base, which has a narrower base. So for the short base, I not only get bigger currents, I get maximum control. And if I were to increase W3 way out, this would essentially become almost horizontal, and I would get no current at all. That's why we say that a bipolar junction transistor cannot be looked upon as two back-to-back p-n junction diodes. There must be intimate contact between the emitter and the collector. Intimate being, well, there's a space, there's a base, but we like to make the base as narrow as possible. And we'll see the limitations on that in just a bit. Okay, so let's actually look at a cartoon of a real device. We have the emitter up here. We have the base, which is buried. We want to make sure that it is pristine and pure. And then we have the collector. This is not quite to scale, because really in a scale diagram, the base would be much narrower than it is shown here. But notice that this is a vertical device. The charge flows from the emitter to the collector. Of course, this is a NPN device, and notice that we make the emitter degenerately doped, the base somewhat less, moderately doped, and the collector lightly doped. Okay, so let's say just a couple of words. This will be more or less qualitative on using the BJT as a current amplifier. I'm going to repeat this diagram that we had a few pages back. This is the one that we're gunning for in forward active mode, where we put the base collector junction into reverse bias, and we get a nice, healthy collector current because the slope is quite high. Now, the basic idea of BJT, in fact, the whole reason that BJT exists, is that we use the input current, which is base to emitter. I should have said base emitter current. let me, I'll correct. This should be the base, the base emitter current should control the collector current, and the collector voltage should not control the collector current. And that is exactly what happens for reverse bias larger than a few, again, this should be a few hundreds of millivolts, not a few volts. You can get up to volts, but we start with a few hundred millivolts. And what happens is contained in this diagram. We have two voltages, VEB and VEC. Now notice that VEC is from emitter to collector. And I should have run another equation here. VEC is equal to VEB plus VBC. And I probably should put that in. These are the characteristics. And what happens here, how do I know this is NPN, by the way? I know it's NPN because I have VCE here. So in PNP, I will have VEC. The emitter is positive, remember that's with forward octave mode, with respect to the collector, which is negative. The first letter generally represents the positive, and the second letter the negative. For a NPN, it's the exact opposite. The collector is positive and the emitter is negative. What happens here is that I do get control of collector current. This is collector current. Here, these curves, I get control of collector current with collector voltage in this region right here. However, after the bias at the base collector junction becomes more than a few hundred millivolts reverse bias, I lose that control of collector voltage versus collector current, and the collector current depends only on the forward bias at the base emitter junction, or the emitter base junction. And here's why. It goes back to here. I can't go less than this point. This point represents the lowest number that this could possibly go to. So let's say it hits this point at 0.7 volts reverse bias, and I go to 20 volts reverse bias, a huge increase. This isn't going to move. There is absolutely no control of the collector current based on the bias that I apply at the base collector junction. So this point right here, I lose control of the collector current based on the collector voltage. And that is exactly what I want. I want the collector current to be controlled only by the forward bias on the emitter base junction. Okay, actually, I'd like to stop right here. We've been going on long enough, and I need to clarify some of these points, specifically why the collector current is controlled only by the base current, or base emitter current. So I want to go back and amplify some of those equations that we saw a few pages back. So let's end here, and we're going to skip all the way down, all the way through all of this stuff here, and we're going to the last video clip. This is from Don Giovanni. All of us have lists. We have sometimes to-do lists at work. We have bucket lists to accomplish before we leave the world. We have grocery lists, but nobody's got a list like Leporello in Mozart's Don Giovanni. This is the ultimate list. Let's listen to Mandamina, sung by Burl Teffel, and enjoy, and we'll see you next time.
Say that the tenor always gets the girl, don't they? Well, Don Giovanni has a list. Leporello, his little sidekick, keeps this book. It makes a grand total of 2,065 ladies. Blondes, brunettes. In the winter, he likes the bigger ladies. In the summer, the smaller ladies. Old, young, he just loves women. Adamina, il catalogo è questo, delle belle che amo il padron mio, un catalogo è che ho fatto io. Osservate, leggete con me, osservate, leggete con me. In Italia 640, in Almania 231, 100 in Francia e Turchia 91, ma in Spagna son già 1.300, 1.400, no, 1.300. Van fra questi contadine, cameriere cittadine, fan contesse baronesse, marchesane, principesse e van donne d'ogni grado, d'ogni forma, d'ogni età, d'ogni forma, d'ogni età. In Italia 640, in Almania 231, 100 in Francia, in Turchia 91, ma in Spagna son già 1.300, 1.300. Van tra queste contadine, cameriere, cittadine, van contesse, baronesse, marchesane, principesse, e van donne d'ogni grado, d'ogni forma, d'ogni età, d'ogni forma, d'ogni età, d'ogni forma, d'ogni età. Nella bionda eglia l'usanza di lodar la gentilezza nella bruna la costanza nella bianca la dolcezza. Vol d'inverno la grassotta, vol d'estate la magrotta, era grande, maestosa, era grande, la piccina, 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 e ogni or vezzosa, e ogni or vezzosa, e ogni or vezzosa. Delle vecchie fa conquista pel piacer di porle in lista a passion predominante e la giovin principiante non si picca se sia ricca, se sia brutta, se sia bella, se sia ricca, brutta, se sia bella. Purché sapete quel che fa? Voi sapete quel che fa, pur che porti la gonnella. Voi sapete quel che fa, voi sapete quel che fa, quel che fa, quel che fa. Voi sapete